Okay, guys, so let's check out finally how one of these confidence intervals for means is going to be constructed. So when the conditions for inference are satisfied, the sampling distribution for your sample means has roughly a normal distribution. Because we don't know your standard deviation of the population, we estimate it by the sample standard deviation. So this I talked about in the first video a little bit. So here's where that idea of a standard error came in. We saw this with our proportions as well. We didn't have our true proportion, our population proportion. What we had to use was our sample proportion. So that's why that formula had p hat in it. And because of that, we couldn't call it a standard deviation. We called it a standard error. The same thing is true here as well. You're using the standard deviation from your sample, not your population, and so it is a standard error. So, much of this is you can already figure out. So we're going to use critical values from the t distribution with n minus 1 degrees of freedom instead of the z critical value. The other idea is that it's a standard error instead of the standard deviation. And so as a formula or what to put in here that's different from when we did our proportions. So our statistic right now is our x bar, so that's your sample mean. Your critical value is now coming from a t distribution, so it's a t critical value, and then your entire standard deviation is now the form that you have to follow for a sample mean, which is given on your reference sheet like this for a sample mean. Okay. Of course, the problem being we do not know our population standard deviation, so we have to use our sample. So here's your standard error here. Okay, so here's our first example, and our only example. We'll do plenty more in class. So environmentalists, government officials, and vehicle manufacturers are all interested in studying the auto exhaust emissions produced by motor vehicles. The major pollutants in auto exhaust from gasoline engines are hydrocarbons, carbon monoxide, and nitrogen oxides. Researchers collected data on the nitrogen oxide levels for a random sample of 40 light-duty engines of the same type. The mean NOx reading was 1.2675 and the standard deviation was 0.3332. Construct and interpret a 95% confidence interval. And then we'll talk about part B. We'll go back to that. Okay, so let's first check our conditions as always. Okay. So I'm going to kind of talk through some of these. So random, okay? They do say that it was a random sample of 40, so we're good with random, okay? Our independence check, okay? That's your 10% condition. We would have to assume that 40 would be less than or equal to 10% of light duty engines. Okay, and then your large sample condition, because it's a mean, so I'm not going to call it a large counts condition anymore. To check for it being normal, we need a large enough sample, and so that we needed n to be greater than or equal to 30, and our sample here is 40, and so our conditions are met. We can construct a confidence interval. Okay, so the first thing that I want to talk about is our t critical value, since that's sort of new to us. Well, we've seen it in the last video. So I'm going to find that by inverse t. By the way, there is a table that has a t distribution, but we don't use that. Technology is more accurate. So we're going to inverse t our area. So it's a 95% confidence interval. So our area is 0.025. Okay, and this is your area, And then your degrees of freedom here is going to be 39. So your degrees of freedom are found by doing your sample size minus 1. 40 minus 1 is 39. You are going to get a t-value of negative 2.023. Of course, it's a confidence interval that we need, so we're going to use the positive. Okay, so let me just get to the next, so I have a nice blank slate. So our sample mean plus or minus, our t-critical value, and our standard error of our mean, okay? They gave you your sample statistic was 1.275 plus or minus. I just found my t-critical value of 2.023, and my sample standard deviation was 0.3332, and my sample size is 40. So last year, some of my students had an issue going back to N, but it's not degrees of freedom here. You are talking about the actual sample size of 40. Okay? And so running through calculations, and we are going to look at it in the calculator as well, you will get a confidence interval of 1.1609 to 1.3741. Now, in its interpretation, it is exactly the same as how you interpret your confidence intervals for proportions. So we are 95% confident that the interval between 1.1609 and 1.3741 captures the true mean level of nitrogen oxides emitted by this type of light-duty engine. So the big difference there is that it is not a true proportion anymore. You've inferenced about a true mean. And that's it. We will have plenty more practice with this in class.